for the past 7 days, we've been dropping questions daily for chemistry daily drills on Instagram and on TikTok, right? So we've dropped the question for 6 days, actually, all right? And I want to use this medium to congratulate the winner for the first week, right, Marianne? All right, congratulations for winning the week 1. All right, so we just rewarded the consistency work, all right? So that's what you need, the skill you need to excel in your JAMB or possibly writing WAEC as well. So we want to quickly provide answers to all the questions dropped so far for day 1, day 2, day 3, day 4, day 5, and day 6. That will make a total of 60 questions, all right? 60 questions drawn from the entire syllabus. You can see that's wonderful. So let's quickly get into it, and I want to believe that you can see it. This is day 1 already, and let's quickly work on the question. The first question says, which of the following can be used to remove oxygen from a sample of hair? Okay, that is alkaline pyrogallo. All right, the answer is what? Alkaline pyrogallo. All right, so let me pick a red pen so I can use it to mark the answer. All right, so that is it. All right, so in case sometimes you can talk about concentrated sodium hydroxide, this one will remove CO2. This is for oxygen. Or ammoniacal brine solution. This is another solution entirely. It's used in solvay process. All right, boric acid. Have you seen this formula before? That is boric acid, H3BO3, which I can also write that way. All right, so the answer is alkaline pyrogallo. If you're removing CO2, that is concentrated sodium hydroxide, will do that for you. Ammoniacal brine solution is used in solvay process to produce washing soda, right? While boric acid is a mild antiseptic. All right, so it's not just like we're picking the answer, we're explaining everything in case you see some other one. Let's go to question 2. Don't want to waste time here. Which of the following is not an isomer of an alkane with 5 carbon atoms? Okay, alkane with 5 carbon atoms. The first one is pentane. Of course, pentane is C5. Can you see? C5. So that is an isomer. It has 5 carbon atoms. This is pentane. All right. When you put everything to be hydrogen. All right. 2-methylbutane. Okay, let's try that again. That is B. 2-methylbutane. 2-methylbutane. 1, 2, 3, 4. All right. Methyl groups attached to carbon number 2. If you put this again, that is also C5 carbon system. All right. So if you look at the pentane, has C5H12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. This is also, so that means that's another isomer. Number 3, 2,2-dimethyl propane. Okay, let's try 1, 2, 3. The methyl group will be here, another one here. So that's the C5 carbon system. And if you look at this again, it's going to be C5H12. Right. Remember, isomers have the same number of the same molecular formula for different structure. So C5H12, all of them here, C5H12. Of course, possibly the answer will be the 3-methylbutane. Of course, 3-methylbutane, as you could see it. Let me try to clean this. Okay. Let me clean this so you can see how we can put that. Great. All right, so 3-methylbutane does not actually exist. All right, some of you will think it's another compound. Look at this, 1, 2, 3, 4. So if I start my count from a 1, 2, 3, 4, I put methyl here. So I would like to now count from here because we count from the end that is closer to the position of the substituent CH3. So what we call 3-methylbutane is actually 2-methylbutane. So 3-methylbutane does not exist. So that's the answer, right? So that's why it's D. We really want to make it fast. Let's go to the question 3 of the 1. The maximum number of electrons that can be accommodated in an orbital is, all right, what people call S orbital, P orbital, D orbital. They are not actually orbitals. They are called subshell. All right. The real orbital is that box you write in. All right. For example, if I say P subshell has 3 orbitals, can you see those 3 boxes? Only 2 electrons can occupy an orbital. Okay, that makes it A. All right. Remember, maybe you're learning for the first time. SPD, they are called subshells, not through the orbitals. All right. But if I say p orbitals, may mean that I mean orbitals in p subshell. But most people think p is the orbital. P is the subshell that has three degenerate orbitals. All right. And each of the boxes can be accommodated by the two electrons. I hope that is clear. All right, all pure samples of the same chemical compound contain the same element combined in the same proportion by mass. This is a statement of what? Law of what? Definite proportion. All right, remember, conservation of matter is another one that has to do with matter can neither be created or destroyed. Why? Multiple proportion and this talking about different elements. If they combine to form more than one compound, several masses of the other. So the answer is actually B, law of definite proportion. It's also called law of constant composition. It means that irrespective of where a compound is formed, let's say, for example, water, you get it from rain, you get it from sweat, all right? You get it from anywhere, anywhere. Let's say river. As long as it is pure, it's going to be H2O and it's going to be combined in the same proportion by mass. That is 2:16, right, which is 1:8. Because it's a compound, it has a fixed ratio by mass. All right, so that is law of constant composition, which is also called the law of definite proportions. I hope that is clear. All right, let's look at the question 5. A particle that contains 9 protons, 10 neutrons, and 10 electrons. Of course, let's say the particle is represented by X, 9 protons, that is it. Okay, so if it has 9 protons, the electron is supposed to be 9 too, if it's neutral. But now electron is 10. It means it has gained 1 electron. Okay, so that will make it minus. All right. And neutron, of course, when you add proton plus neutron, you get the mass number. 10 plus 9. We don't need that though, but I'm just telling you that. All right, so proton plus neutron, 10 plus 9 will give you mass number up there. So this is proton number. Electron is supposed to be 9, but because it is 10, it shows that it has gained 1 electron. So it's a negative ion. All right, and that's why this is the answer. So let's go to question 6 first. All right, if the distance between the nuclei of chlorine atoms, nuclear, okay, that's the plural of nucleus. This is the chlorine atom, this is another chlorine atom. All right, it look like that. So chlorine, chlorine. The nucleus, the distance between, that is internuclear distance, is 0.194. So what will be the distance between them? That is the atomic radius. All right, atomic radius is from here to this guy. So of course, you can see that that will be 0.194 divided by 2 nanometer. All right, you know why? They say the distance between nucleus and another one, it looks like diameter. Diameter is though a circle like this. All right, but now we bring two atoms together. I hope you can see that. And that is it. So it looks from. So now, if you divide it, you get the atomic radius. All right. So just divide this by 2, you get 0.02 in 19. That is 9, 14, 7. Okay, so that's the answer. Answer is A there, right? So let's look at the question 7. Sodium triisocarbonate 4 decahydrate decreases in mass when exposed to the atmosphere. The phenomenon is called what? All right, this is sodium triisocarbonate 4. Decahydrate means H2O. All right, some of you don't know. Deca is 10. All right, let's say it's copper tetrasulfate 6. This is H2O will now be what? Pentahydrate. That's lovely. All right, cobalt 2 chloride, hexahydrate. These are just stuff like you should know. What's the color of this? This is white. It's not art, but I'm just telling you. This is blue, and this is what? This is pink in color. But I will use this guy, an hydrous form, to test for water. Let's see. So, but when you expose it to atmosphere, it decreases in mass. That means it's losing this water crystallization, and that process is called efflorescence. All right, that is efflorescence. All right. So when you expose it to the atmosphere, let's say you place it on a digital balance, all right, and then you expose it, you see that it keeps reducing in mass because it tends to lose this water oxidized. So you can lose up to the entire stuff or even 9 out of this. All right, so sometimes you may see the equation like this. Just know that it's the same thing they are talking about. H2, maybe 10. You now see minus 9H2O. We now have Na2CO3 dot H2O. So out of the 10, you have lost 9. So this is still efflorescence. Hygroscopy means that it absorbs, there are some substances that absorb, they absorb water from the atmosphere and they get sticky if they are solid. They don't absorb so much. That is hygroscopic substance, just like CO. All right. Effervescence is not in this category. It's a situation where, let's say, a gas is giving off. Let me say example, like when acid reacts with carbonate, there is this, the gas will bubble through the water and stir everywhere. So that is what we call effervescence. It's like you open your fizzy drinks like Coca-Cola or 7-Up. You can see that gas. So that's like effervescence. It's not part of them. So hygroscopy absorbs water, but just little amount of water. The liquid sense absorbs so much water, like NaOH, and it dissolves in it. All right. While fluorescence gives out water. All right. So the answer is D. All right. What current would deposit this? This is electrolysis. All right. Listen, I'll give you mass equals quantity times relative atomic mass times the charge Friday. This particular formula, please, it works wonders. You can solve your electrolysis calculation and so many of it. All right, can solve so many of it. So please don't take it for granted. What is Q? Q equals I times T. That is current times time. Current in ampere, time in seconds. This is relative atomic mass. This is the charge being transferred. In the case of zinc 2 plus, the 2 plus will gain 2 electrons, all right, to be deposited as zinc at the cathode. So that means our N equals to 2, all right. If you are dealing with sodium now, that's charge of 1, N will be 1. If you are dealing with copper 2 plus, it will be 2. If you are dealing with magnesium, will be 2 again, because 2 plus. If you are dealing with aluminum, will be 3. So that is the value of N. But this is zinc, N is 2. This is the mass which has been given, 3.25 gram. We give you quantity is current times time. So our current is I times time. Time is 2 hours. So 2 times 60 minutes, 60 minutes times 60 seconds. That is 3,600, but let me leave it that way. Then relative atomic mass for zinc is given 65, all right? I was wondering, well, if it's this actual jam question. So N is 2 times 96500. So let's make I the subject and let's see what we get. So that is 3.25 times 2 times 96500 over 2 times 60 times 60 times 65. Puncture your calculator. Puncture. Let's do that. That will be 1.34 ampere. Okay, so that is correct. So number 9. All right. Which of the following will form a precipitate with ammoniacal solution of copper 1 chloride? All right. This particular ammoniacal solution of copper 1 chloride is a very important, let me call it, reagent. All right, because when we talk about alkanes basically undergo substitution reaction and combustion. All right, it doesn't undergo addition reaction because it's saturated. But alkenes and alkynes are always dragging. Do you understand that language of mine? I say alkenes and alkynes. Let me write it properly because of the all right, and alkynes. All right. I always like whatever you can do, I can do. It's just like what a man can do, a woman can do it. Okay. Akin is like I don't want to be gender oversensitive or sensitive. Let me say Akin is like woman, for some reason, kind men. All right. So Akin will say what a man can do, a woman can as well do. All right, claiming that. All right, of course. Akin will react with hydrogen. This one will react with hydrogen. Chlorine, this one will react with chlorine as well. Combustion, this one will do combustion again. Dechlorize bromine water. Alkynes will also do the same. All right. Then come this particular ammoniacal solution of copper 1 chloride. Alkenes cannot react with it. All right. But alkynes do. All right. They form a metallic derivative, colored substance when you a precipitate is formed when you react them. But of course, it's not all alkynes that behave like that too. So we are just telling you that ethene cannot do it because it's alkene. This is another alkene cannot do it, but these are alkynes. The two are alkynes. So not all alkynes will form a precipitate, a metallic derivative with copper 1 chloride in ammoniacal solution. All right. So the difference is the only alkyne that has the triple bond at the end of the chain. All right. Something like, look at this. Ethine only has two carbons. So of course, this is terminal alkyne too. The triple bond is at the end of the carbon. Now, if you look at prop 1-ine, prop 1-ine is 1, 2, 3. So this one is terminal alkyne because the triple bond is at the end of the chain. All right. Look at but2-ine. But2-ine is not a terminal alkyne. Look at this. The triple bond is at the position 2, 1, 2. So it's not at the end. So only alkynes that have the triple bond at the end of the chain can form a precipitate with this reagent. I hope that is understood. So we call them terminal alkynes. Okay. So I hope that is clear. So which one is the answer now? It's only prop 1-ine because it's terminal. It has the triple bond at the end of the chain, and those are the ones that form that. So let's say the last one. Wow, this is about the IUPAC nomenclature. All right, and I want you to see the compound where we can zoom it. All right, well, first of all, we look for the longest continuous chain. Somebody can name from a 1, 2, you go 3, 4. We keep like that. One can go 1, 2, and say 3, 4, 5, 6, 7. Wow. All right. Another person can go like this. Let me pick another color of pen for that. 1, 2, 3, 4, 5, 6, 7. So another one can go 1, 2, 3, 4, 5, 6. Instead of 7, go 8, what? 9. I hope you have seen that. So different ways you can do that. Another one can say 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I think the answer is not even here, isn't it? Okay, let's try to see if the longest chain. Okay, the answer is not there. It's from a particular question. 1, 2, 3, 4, 5, 6, 7, 8. Oh, the answer is there. Look at this very well. I want you to please take note. I've been able to count. Maybe you're not seeing what I'm seeing clearly. So let me see if I can increase or let me rewrite the structure so you can see that. Look at this carbon. H3C is here. All right. Then next to this is C2H5. Okay. Can you see that? I was thinking they didn't put the answer there because I saw the number of carbon that. So this is 1, 2. This is another one. I'm on this one that I wrote 3 here. This is another one. That one has CH3 here. Then I have another one. That one has H before the double bond. Then C. All right. Then CH3. So actually, the longest chain will be here. Let me show you where the longest chain will be. Will be from here. Can you see that? So you keep working on carbon together. So this is 1, 2, 3, 4, 5, 6, 7, 8. So 8 is the I named from there because of the fact that the double bond is closer to that end. If I move from 1 to 3 like this, the double bond will be around 1, 2, 3, 4, 5, 6. So we name from that end that is closer to the position of the functional group, which is the double bond. So we have the parent chain, which is the longest chain, as 8. That makes it octene. All right. So that is octene. But the double bond is at position 2, so octuene. So the answer has actually come out here. That is how you be fast if you're writing JAMB. All right, and just speak it right away. But let's see whether the names there are consistent. 1, 2, 3, 4. Methyl group is there. Methyl group is there. Methyl group is there. All right. So one position 4, another one position 6, another. So that is 4, 6, 6. Trimethyl octuene. All right. So if you need so many other compounds I'm going to give you, you can drop the answer in the comment section. So we'll be able to show you that. All right. So this is the end of day 1, and we are still going to day 6. That is really, really great. So those of you that put the answers, you can now begin to check and score yourself in the comment section. Just put a score. Like, I got this. You mark your score by yourself. So let's go to day 2. All right, day 2, we have all these questions as well. So which of the following explains the behavior of electrons in an orbital using quantum numbers? All right, which of the following explains the behavior? That is Pauli exclusion principle. No two electrons have the same values of all the 4 quantum numbers. All right, so that is that. If you want to talk about Albert principle, that is when feeding electrons into orbitals, we fill the lower energy first before the higher one. So I'll pick the answer. That is it. Holmes rule is also about the filling singly before the pairing takes place. All right, difference between an acid and its conjugate base is, all right, an acid and a conjugate base. That is, let's just talk about this. In definition of an acid, if I say what is an acid, the answer should not be like just jump into it. You ask me which method, which law, which principle, all right, are we following to define your acid? Because we have Arrhenius, all right, we have Bronsted-Lowry concept, and we have Lewis concept, all right. So have I made a video anywhere around here? So when you say an acid is a substance which dissolves in water to give hydrogen ion or hydrogenium ion, you're actually talking about Arrhenius, all right. So Bronsted-Lowry is about the acid being a proton donor, all right, and a base being a proton acceptor, all right. So let's say we have CH3COH. So if you donate this proton, this hydrogen ion here, all right, so that is an acid. Okay, this is an acid. So its conjugate base will be the one without this hydrogen plus. All right. So the difference between this and COO, that is COO I wrote there, COO minus. All right. Let me pick the pen right. All right. All right. So this is the acid, this is the conjugate base. So the only difference is the proton. Why is this called a proton? Hydrogen is 1 1. Proton is 1. Electron is supposed to be 1, but it has lost 1 minus 1 0. Neutron is 1 minus 1 0. So it's only thing proton. So hydrogen ion is called proton. So it's only proton that makes the difference between acid and the conjugate base. If they say HCl, what is the conjugate base? Cl minus. So this is the conjugate base of this acid. All right. So let's go to question 2. Maximum number of electrons that can be accommodated by an M shell in an atom. All right, so the first shell closest to the nucleus, we call it K, the next one L, the next one M, the next one N. And we assign the N. N is actually the principal quantum number 1, 2, 3, 4. What it means in a nutshell is N is 1 means the first shell. That is K, the second shell, the third shell. All right, so we usually use the number, what's the formula? That is 2n squared to calculate the maximum number of electrons that can be accommodated in each of these shells. All right, so n is 3, okay, for M shell. So you say 2, 3 squared. That is 2 times 9, which is 18. So that means this guy can accommodate up to 18 electrons. If it is this one, that is 2, 1 squared. That is 2. If it is the second one, 2, 2 squared, that's 2 times 4, which is 8. The other one, 2, 4 squared, that is 32. I hope you can get that. So the answer is what? Is 18. All right, if you pick something else, please take note. How many unpaired electrons is present in copper 2 ions? All right. You must know, if you're writing WAEC or JAMB, that you must know your first 30 elements, not just first 20. Please, first 30 elements. So this is number 29. That is copper is number 29. Right, so let's write the electron configuration for copper. I'll use argon for 18. That is 1s2, 2s2, 2p6, 3s2, 3p6. All right. So 4s1 and 3d10. This is actually the electronic configuration for copper. But if it's now copper 2 plus, that means it has lost 2 electrons. So you lose 1 electron from here, and you lose another one from here. All right, so it becomes argon 4s0 3d9. So how do we undo 3d9? We have 5 degenerate orbitals. All right, 1, 2, 3, 4, 5. Filling it singly first, that is untrue before pairing takes place. So we have one unpaired electrons. You can see how easy it is. So first of all, you write the electronic configuration. Then you try to see if the last orbital you're working with has the degenerate orbitals, and you follow on through to line the electrons you're filling into those orbitals. Right. Also take note why you are losing electron. You are losing electron first from 4s before 3d. All right, let's go to question 5. Which of the following differentiate two isotopes? And what are isotopes? Isotopes are atoms of the same element with the same atomic number. Let me even use chlorine straight away to the same atomic number or proton number, but different mass numbers. Okay, like this is like isotopes of chlorine. You'll see that they have the same number of protons, which is the number of protons. Number of electrons will be the same as well because protons and electrons they are equal for neutral atoms. Number of electrons in the outermost shell. Of course, if this is 281, okay, 287, this one will be 287 as well. So that makes it number of electrons in the atomic number to be the same. So of course, the D will be the answer since you are sure that this is correct, this is correct, this is correct. But number of neutrons, if you want to get number of neutrons, subtract this 5 minus 17, 7 minus 7. So this one has 18 neutrons. This has 20 neutrons. 37 minus 17 is 20. 35 minus 17 is 18. So they have number of neutrons. In fact, we can define isotopes as the atoms of the same element with the same proton number but different number of neutrons. All right, so mass number of different. Question 6 of day 2. Which of the following explains why the size of atoms decreases across any period in the periodic table? Okay, so let me start from sodium. Let's look at sodium, magnesium, aluminum. All right, so like that. All right, this is 281. That is in period what? 282, 283. That is period what? That is period 3 because they have 3 shells. All right, 2, 8, 1. All right, what we're saying is that as you're moving across, the size decreases. You know what it means? We are saying that sodium atom is bigger than aluminum atom, despite the fact that sodium is 11 and aluminum is 13. That's what we're saying. If you mean move across the period and the size of atoms decreases across the period, what it means is sodium is bigger than aluminum. And sodium has 11 uh, protons, while aluminum has 13 protons. So you can see, let's now see why is that? Why is that? All right, let's quickly compare them. 281, all right? So that is sodium. That is sodium, 281. And aluminum is also 281. Can you see that? So if you look at this, it's basically supposed to be the same size because it's three shells for each of the sodium and aluminum. All right, sodium and aluminum, they have 3 shells. But now, if you look at sodium, sodium has 11 protons inside it, while aluminum has 13 protons inside. So because neutron is not charged, so nucleus is positively charged. So that positive charge is attracting all these electrons in this shell to itself. So therefore pulling. So which one will exert the more attractive force? Is it aluminum, which is 13 plus, or sodium, which is 11 plus? Of course, 13 plus will have a strong attractive pull, all right, because it's stronger. Just think of it as a magnet. Plus 13 powerful and 11 powerful. So you see that 13 will pull the tall shell closer to itself. So therefore shrink the size of the atom. So as you are moving across the period, there is increased positive nuclear charge. All right, and that is that's the answer, right? So that is just the answer. The rest are just to distract you. Let's move. All right, question 7. Which of the following is not true of 2,2-dimethylpropane? All right, let's quickly write 2,2-dimethylpropane. 2,2-dimethylpropane. That is the structure. All right, this is CH3. That is the dimethyl CH3. Then we have all that. All right, can you see that? So this is 2,2-dimethyl. When they give you something like that, quickly write it somewhere and make sure that you do what you're supposed to do. All right. Which of the following is not true of 2,2-dimethylpropane? That's the question. It is an isomer of 2-methylbutane. Okay, let's look at this. How many carbon do you have here? We have C4, then H what? H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C4, C5H12. All right, C5H12. So 2-methylbutane is 1, 2, 3, 4. Then methyl will be here. Say 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is also C5H12. All right. So that means this is correct. It's true. It's an isomer. Isomer, they have the same molecular formula, C5H12, but different structure. All right. So it has 12 hydrogen atoms per molecule. This is 12 again. That means that is also correct. Is that the same empirical formula as N-pentane? Okay, N-pentane is 1, 2, 3, 4, 5. All right, the H will be 12, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is CC5H12. And the empirical formula, this is the molecular formula and also empirical formula because molecular formula shows the actual number of atoms in a molecule, while the empirical formula shows the simplest whole number ratio. This is still empirical formula. Molecular formula and empirical formula can be the same. For example, water, that's the actual number of atoms, which is molecular formula. This is also empirical formula, which is the simplest whole number ratio. So we have that correct as well. So that shows that this is not going to be the wrong answer. But let's see. It has one lone pair of electrons. Hydrocarbons don't have lone pair because all the bonds must be bonded with hydrocarbons, hydrogen and carbon. No lone pairs. Just take it as a rule. There is no lone pair of electrons because all the electrons around carbon and hydrogen have been used up. All right, so that is the answer. So let's look at question 8. Calculate the mass of sodium or hydroxide pellet required to prepare that. All right, so let's see that. Sodium, that is NaOH, molecular mass will be 23 plus 16 plus 1. That is 40 gram per mole. All right, so we have our volume to be 250 cm cube, which we can divide by 1000 to get 0.25 dm cube. All right, so the concentration as well is 0.10 mole per dm cube. So calculate the mass. First of all, you get your N. N equals CV. C is 0.10 times what about volume? 0.25. Can you see that? 0.10 times 0.25. That is CV. N equals to CV, isn't it? So what will be the concentration is 0.1 and that one. Okay. So the decimal is just 1 here, 0.1 times 0.25. So the answer is 25. Then we have 3 decimals there. So 0.25. That is number of moles. Don't mind me. Use your calculator. All right. I love playing with figures. So let's use that calculator so that you can be sure that that is the answer. All right. So that is 0.1 times 25. Can you press it with me? 0.1 times 0.25. So 0.025 mole. All right. So you now say number of molecules mass over molar mass. All right. So we just multiply that by 40. So M will be 40 times 0.025. So what's that? So that is 1 gram. Okay. All right. That's 1 gram. So the answer is this. So that is the mass. Let's look at another one. Which of the following is a tertiary alkanol? For you to know tertiary alkanol, let me quickly do that. Alkanol has OH group as the functional group, all right? So the carbon carrying this hydroxy group, which is OH group, if it's only one carbon that is attached to it, let's say the rest are hydrogen. Okay, if it's only one carbon, so that is the primary. If you have 2 carbons attached to the carbon that is carrying the hydroxy group, can you see the rest will be H? That is secondary. If you have three carbons, atoms attached to the carbon carrying the hydroxyl group, then that is tertiary alkanol. All right. Primary, secondary, and tertiary alkanol. So they say which of the following is a tertiary alkanol? Ethanol. Let's see if ethanol, for example, ethanol is just C2OH. All right. That is that H H H H H. So you can see the OH, only one carbon is attached to the carbon that is carrying the hydrogen. That means ethanol is a primary alkanol. Let's look at butan-2-ol. Butan-2-ol will be like this fragment. 2-ol, that is OH attached to carbon number 2. Okay, OH is attached to carbon number 2. This carbon carrying the hydrogen, 1 and 2 carbon, the rest will be hydrogen. So that is secondary alkanol. 2, 2, 3 trimethyl heptane 1-ol. When you see 1-ol, that is a primary alkanol. I will show you the reason. How many carbons? 7. 1, 2, 3, 4, 5, 6, 7. Okay, this is carrying OH. Now, because this is first carbon, second carbon, okay, second carbon. All right, so the second carbon is carrying the methyl group, so CH3. All right, the second carbon is still carrying another methyl group, CH3. That's why it's the third one is carrying CH3. Can you see? But if you look at the carbon carrying the OH group here, you will see that only one carbon, which is this one, is attached to it directly. All right, because if I want to draw that structure, maybe I should draw it, because some of you will be so like, how I don't get this. All right, let's just look at it. I will write the full structure of that guy. All right, so let's see how to go about that now. All right, the full structure of heptane. Let's see. Okay, let's see. Okay, so let me pull that. That is heptane 1, 2, 3, 4, 5, 6, 7. That is heptane. All right, this is OH because it's first carbon. So put H here, put H. Second carbon is carrying methyl group, another methyl group. The third carbon is carrying methyl group. All right. So, but let's just leave the rest of the stuff. Look at the OH group here. This is the carbon. How many carbon atoms are directly attached to this? Only one. This is the one that is directly attached to this group. Okay. So that is not. Okay. So that is not. That is also a primary alkanol. All right. So this is not. This is not. This is not. So let's see 2-methylpropan-2-ol. All right. Of course, that will be the answer. But let's see whether that is true. Propan has 1, 2, 3. 2-methyl. OH is there at the propan 2 or 2, then CH3. You can see that 1, 2, 3 C are attached to the carbon that is carrying the OH. And that's what makes it a tertiary alkanol. All right, so the next one is question 10. Which of the following covalent bonds has 2 lone pairs and 2 bond pairs of electrons? All right. As a rule, I've told you that there is no lone pair in alkane in hydrocarbon. So let's run this because all the bonds are being used by carbon and hydrogen, central carbon. Look at that. So in water molecules, let's see. O is 6. All right, that is 2, 4. O is 8. That is 2, 6. Okay. Number 8, 2, 6. So let's see. This is O. All right. 1, 2, 3, 4, 5, 6. All right. Remember inside we have 2, but we don't take care of that. That is it. Then hydrogen will bring its own electron star. That is dot and cross diagram. That is it. Okay. Hydrogen. So you can see that hydrogen, it looks like this. O bond with hydrogen and bond, because this line bond, it takes 2 electrons, the covalent bond, one from the hydrogen and one from oxygen. This second one from oxygen and one from hydrogen. All right. Then you see these electrons are not used in forming bond. They are called lone pairs. So these are 2 bond pairs and 2 lone pairs. And that is water as an example. For example, let me just give you ammonia and see if you know what, just to illustrate that. Ammonia is 2, 5. That is number 7. All right. That means it's going to have 5 electrons in the atom shell. All right, so let's do like this. 5 nitrogen. 1 again, 2, 3, 4, 5. So hydrogen will bring this to form one bond pair, another one bond pair. That is shared pair of electron, which is so you can see that ammonia has three bond pairs and one lone pair. So it's not. All right, so let's move. So you can go and learn more about the dot and cross diagram because the question, the jump and work, they come out there. All right. So we are on day three. We still have a long way to go. So solution to this question. So number one, the shape of an s orbital is spherical. All right, it looks like this. All right, P is dumbbell. All right, so this is S, this is P. Okay, so if D is like double dumbbell. All right, so let's make the answer so quick. It's spherical. If they mention P, that is the dumbbell shape. All right. Number two, which of the following molecules has a triple bond between its atoms? All right. Most of all the diatomic molecules like F2, Cl2, I2, Br2, all right, they are like single bonded. All right. All those halogen, they have single bonded uh, covalent bond. Can you see that? But oxygen is represented as this. Please take note. All right, under dot and cross diagram, we have learned that. And nitrogen is triple bonded to each other. All right, that's why nitrogen is like basically not reactive. All right, it's present in the atmosphere in very high percentage. If it's not there, oxygen of 21% will have dealt with us. So it's a diluent that is trying to calm oxygen down from getting everywhere burnt. All right. So nitrogen is the one that has triple bond, while oxygen double bond. All right. Most of the other ones like hydrogen, or the other gas, it's H. All right. So single bonded to one another. All right. So question three. All right. What's the name of the ester formed when ethanoic acid is reacted with propanol in the presence of this type of reaction is called esterification reaction. So we have the ethanoic acid. Ethanoic acid is CH3COOH plus propanol C2H5 CH3. Let me write this thing very easily for you to understand it, so that you know that is propanol. All right, it's very easy to write. Propanol, just write CH3. That is 3C CH2 CH2OH. Can you see that? So we have 3C there. All right, think of it as this one has lost the OH and this one has lost the H. So what you have left is CH3CO, then another O is there, O, then CH2, CH2, CH3. Look at this fragment. That is it here. Then CH3O, that is it. So this is the ester form plus water. So whenever you react ethanoic acid, this is ethanoic acid, this is propanol. So you form, the first name of ester comes from the alkanol used or alcohol used. Okay, the first what? The first name of ester comes from that. So propanol will be propyl. You can see that this is propyl. This is ethanoic acid, propylethanoate. Okay, so that's the name of the ester form. Propyl from propanol, ethanoate from ethanoic acid. You can see propylethanoate. So let's see if it were to be methanoic acid. Methanoic acid plus ethanol. Okay. Okay, so you can see that, let's say OH is lost here and H is lost here. That is water. So what is left? Combine them. You get HCO, right? Then another O, then C2H5. All right, this C2H5, ethanol, that will be ethyl. Can you see? Then this is methanoic acid, methanoate. So that is how to name ester. So it's very easy. You need more stuff on that. I'll make a video for you. All right. So which of the following scientists is popularly known for his oil drop experiment? That is Millikan. All right, he determined the charge to mass ratio. No, he actually used charge to mass ratio to determine the charge on the electron. All right, someone else, I think Rutherford has done that. It's the one that's determined the charge to mass ratio. But I think J.J. Thomson discover electron, right? Okay, then the Chadwick neutron. Okay, so Millikan, this Robert Millikan was the one that determined popularly known for his oil drop experiment and determined the charge on the electron. All right, so please take note of that. All right, so which quantum number determines the orientation and the degeneracy? Degeneracy. All right, let's start from the principal quantum number. Is it here? All right. So principal quantum number is denoted by n. It determines the energy level. That is K, all those one, n, those one. Then the azimuthal is also called subsidiary. All right. It determines the shape of orbitals. While the magnetic quantum number determines the degeneracy. All right. Let's say p orbital has three degenerate orbitals like this. P sub shell has this. So that is what we call magnetic quantum number. All right, so that's the answer. All right, the first one, spin, is the one that talks about in an orbital. One electron faces up and the other one faces down because of to minimize repulsion. So the answer is magnetic quantum numbers. Okay, the spin quantum number is in both A and C. All right, that should be a mistake there. All right, so the answer is D. All right, so the following are characteristics of transition metals. All right, transition metals are found between group two. Look at the way periodic table is shaped. I hope you know that. So group one and group two are here. So then we have 10 set of, this is the first transition series. There are 10 here from scandium to zinc. All right, before you go into the rest like this. So the between group two and group three, we have transition metals. All right. So for your level, you only need to talk about the scandium to zinc. You must know them. All right. So they have some properties that are characteristic of transition metals. All right, because they are metals generally. So you can say that they are sonorous. What does that mean when we say something is sonorous? I mean, they give off notes, a sound when you hit them, right? So they are ductile. What does that mean? I mean, these are general properties of metals, including transition metals. That means they can be drawn into thin wire. They are malleable. That means can be hammered into sheet. Okay. They have a high metallic luster. That means they are lustrous. They're shining. They have shiny surface. This is also a form of a refractive index. All right. So I'm just telling you so that you remember that. But there are some properties, all those high melting point, high boiling point, that's general properties of metals. There are some properties that are unique for transition metals. That those metals that are found between group two and group three of the periodic table. And look at it, they have variable oxygen states. That's true. If you look at iron, 2 plus, 3 plus, can you see that plus 2 plus? If you see manganese, it has from 7 plus, -4, -5. All right, they form complex ion in solution. Please take note. These are the properties that are uniquely attributed to transition metals. They exhibit catalytic properties. That is also true. That is also true. You know why? This is not true. The D is the answer. All right, set. So I want to talk about the catalytic properties. Okay. If you look at Haber process, what's the catalyst used? It's finely divided ion catalyst. Hydrogenation of oil to produce margarine. That is nickel catalyst. All right. In contact process for producing what? Concentrated sulfuric acid. That is vanadium 5 oxide, a compound of vanadium. You can see that all of these, they are transition metals or they are compounds. So they have that high catalytic properties. Okay, so I hope that is clear too. So let's move to the next one. Concentrated tetrasulfuric acid is manufactured industrially by. I just mentioned that. All right, that means that I've mentioned most of the questions they will ask you in your exam. All right, let's really go into that. Which substance is produced industrially by Haber process? That is ammonia. What about Ostwald process? Most of you don't know. It's concentrated HNO3. Nitric acid, triazonitrate acid. Actually, oxidation of ammonia is what produces triazonitrate 5, and that is Ostwald process. First of all, you write ammonia with oxygen, you form NO. NO with more oxygen, you form NO2. You now dissolve NO2 in water in the presence of oxygen to now form HNO3. Okay, so that is oxidation of ammonia will produce that. Contact process is H2SO4. What about fract process? That is extraction of sulfur. All right, sulfur can be extracted from underground deposits. It has a very low melting point, just above 100. All right, so when you pump in superheated steam, all right, that is a bit a boil higher than 100, so it's going to melt it because around 114 degrees Celsius, and you pump it out. All right, cool it, and it looks like this color, yellow. That color in Haber process. So that's how sulfur. So it's called fract process. All right. So don't forget that. If 50 cm cube, hmm, 50 cm cube of hydrogen is sparked. Okay, this doesn't want to stay. All right, 50 cm cube of hydrogen is sparked. All right, let's look at the next question, which is number 8. All right, 50 cm cube of hydrogen is packed with 40 cm cube of oxygen at that temperature, and the resulting gases are passed through alkaline pyrogalol. All right. So, what volume of the gas is absorbed by that solution? All right. So, let's write the equation first. H2 plus O2 will give you H2. So, we have 2, we have 2. So, that is 2:1 ratio 2. When gases react, they do so. All of these are gases. You can see the temperature is 150. That is not to boil up the water into vapor. So when gases react, they make use of their volume. That means 2 volume or 2 cm cube of hydrogen will react only with 1 cm cube of this to produce 2 cm cube. Have you seen when you add 2 to 1 and the answer is 2? So that is chemistry for you. When gases react, they do so in volume because another substance has been formed. And what I'm saying is, let me show you this. This is 2 cm cube of hydrogen. Okay, let's say we add it with 1 cm cube. Look at where I put the level of oxygen. Okay, then they will mix together. Hydrogen will be destroyed, oxygen will be destroyed, and they will transform themselves into steam. All right, and it's going to be that volume too. All right, it's not going to be 3 because the new substance occupies new volume and has different mass and stuff like that. So when gases react, they do so by this their volume ratio. Okay, so which is a stoichiometric ratio. So that's what it is. So if 2 cm cube of hydrogen will pick this, so but they started with 50 of hydrogen. Look at this, 50 cm cube of hydrogen and what? And 40 of this. So of course, 50 cm cube of hydrogen, we only pick 25 of this to produce 50 of steam because we are talking about 2:1 ratio 2. That's the ratio in which they react. So you see that 50 cm cube of steam will be produced, all right? But now only 25 of the oxygen will be used up because the ratio of hydrogen to oxygen must be 2:1, and that's all. So that means when you mix these two together, you are still going to have, if you produce 50 of steam, you still have 15 of oxygen gas there. All right. Do you understand? Because only 25 will react, so 15 will be unreacted oxygen. So we call it XX oxygen. All right. So we have the total gas there, 50 for steam, 15 for oxygen. So if you pass this through alkaline pyrogalol will just go for oxygen alone. Okay. So oxygen alone. So only this 15 will be absorbed by this gas. All right. I hope you know alkaline pyrogalol solution takes oxygen, just has that affinity for oxygen. So only 15 will be absorbed by that solution. All right. While we have 50 left. Right. So few drops of water was added to anhydrous cobalt chloride. All right. The color of the solid will change. All right. This is a test for the presence of water. This is a test for the presence of water, and we use two different substances to do that. All right, because we are learning. Anhydrous, the one that doesn't have water. Okay, when you add water to it, this is white. It's not pure white, but we just prefer to call it white. Okay, when you have seen it for anhydrous, it's not really pure white, but because copper is there, so white. So when you add water to it, it turns blue because it will pick up 5H2O. So this is blue. Okay, now cobalt chloride too, CCl2, is blue in color. You can see why I started from this because you end with blue And this is actually blue in color for particular. When you add water to it, it forms, it takes 6 molecules of water. So it turns pink. So what's the answer now? That is blue to pink. Can you see that? Please take note of this. Don't forget this. Don't forget this. All right. It's very important for you to see that. All right. So let's move to another one. Which of the following is a D block element? All you need to know is know your scandium to zinc. That is 21. Let me say for you scandium. Okay, let me use scandium, titanium, vanadium, chromium, manganese. Okay, copper, nickel, copper, zinc. This is from 21 to 30. Have you seen them? So this is the one that they can conveniently ask you. Okay, apart from the regular one that you know. Okay, if they tell you now what's the symbol of silver, you must know it. Okay, and it's not within the first 30. All right, so it must those are special elements that you've been working with. If they say gold, you must know that it's AU. But they can't ask what is the atomic number of gold. All right, what is the atomic number of silver? They say mercury, AG, you should know that. Okay, so those are the kind of things. So which of the following? These are D block elements. All these elements from 21, please take note, 21 to 30, that's the gist. Element from after 20 is calcium, so that you know what I'm talking about. Hydrogen 1, you get to calcium. So from 21 to 30, these are the 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Zinc is 30, right? Scandium is 21. From 21 to 30, they are D block elements. So which one is, can you say? This one is okay, they use this one as a distraction. That is group 0. So iron is a D block element. Group 8 is krypton, all right? So I hope we're good to go. So we are moving now. So we 4 already, day 4. So let's see, real gases deviate from ideal behavior. All right. Look at this. When we talk about the postulation of the kinetic theory of gases, all right, gases, they do this and that. That is for ideal gas. Gas in our head, like they should just travel. Once you open them, they move from one place to the other. There is no form of attraction between them. All right. So that is gases should be like this. All right. So that is what gases are known to do. All right. So if truly this is gas, so that is what we have in our head as ideal gas. That is their property. But real gases, we can condition them to behave like something else, that they will not be far apart. What are we going to do? We're going to push them down here together. All those ones, like let me say I push all these gas down. That means I compress them under pressure. So that means high pressure, okay, will make them close together, and there will be form of an interaction which is negligible in the kinetic theory of gases. I hope you're getting it. So because pressure is high, it brings them closer. So they are no longer behaving as ideal position. And then if the temperature is low as well, low temperature will not make them to gain enough energy so that they separate from one another. So low temperature and high pressure will make the combination that will make the real gases to deviate from the ideal behavior. So that is D. I hope you got that gist. Okay, should. So let's move to question 2. The following molecules are linear in shape, except, okay, like I've told you that hydrogen is like this, oxygen is like this. Okay. Water, oh, you may want to know. Water is meant to be like this. Okay. And CO2. But there is something that is playing part here. We call it a particular law. We call it valence shell electron pair repulsion theory. Can you say valence shell electron pair repulsion theory? All right. What it means is just like the bonds used to making coming between the atoms. Those bonds don't like one another, all right, because electrons are used in forming those bonds. Those electrons, they repel one another, all right, they don't want to touch. So they want to stay apart, as far apart as possible from one another. Don't stay close to me. So let's say we have a bond here, hydrogen and hydrogen. The way they can stay is actually H to H. That's the way they can stay apart. All right, can't bend it. All right, oxygen also this way. Now look at water. Water is supposed to be able to stay as apart as possible like this as well. But something is coming into play here. All right, I drew the water for you. I said oxygen has one, two lone pairs of electrons. Then we now have hydrogen. Okay, so there is a repulsion. I'm representing this lone pair like this so that it looks like one. So there is a repulsion between lone pair. That's the highest. They push each other away because they are free now. They are not bound to anything. So the repulsion between lone pair and lone pair is very high. So it's greater than between lone pair and bond pair, which is next to it. Then bond lone pair and bond pair. Then the least of it is bond pair to bond pair. Look at that. All right. So what we're trying to say is just like instead of the water to just stay like this lone pair pushes each other and this one push and they distort the structure. That's why we call water bent, okay, or V shape. All right, the lone pair of electron is what causes this. All right, everything here is just right from this direction. The lone pair and the bonds they are playing in a straight line. So that is why that is bent. All right, I hope that is clear. So let's go to the next question. Question 3. Which of the following organic acid is present in grapes? Which of the following is present in grapes? The one that is present in grapes is tartaric acid. All right, tartaric acid. Sometimes ascorbic acid is citrus fruit like lemon, oranges. Lactic is from spoiled milk or sour milk. Ethanoic acid is vinegar. All right, so take note of that. It's important. If I tell you palmitic acid from palm oil, oleic acid from olive oil, all right, we have so many of them like that. Okay, so which of the following laws is used to explain balancing of chemical equation? Let me just try to ask you, what would an unbalanced chemical equation mean to you? All right, this is not balanced now. If you look at it before the arrow, hydrogen is 2, oxygen is 2. But after the arrow product side, hydrogen is 2, oxygen is 1. All right, it means that we have destroyed oxygen atom. So where did it go? So an unbalanced chemical equation will mean that atoms has been either created or destroyed. All right, if I have more atoms in the product side, that means I've created it. But here I've destroyed one atom of oxygen. Where did it go? No, you can't just destroy it to be transformed to another thing. If at all you were even talking about reductive. So that's why we must balance it. So which of them states that atoms can neither be created nor destroyed? All right, so that is the conservation of matter. Remember, definite proportion, we treated it some days ago. All right, the main ore of tin is calciterite. Maybe you don't even know that tin is Sn. It's tannum, derived from the Latin name. This is the formula for calciterite. The one for hematite is for iron. All right, you can see that when you get hemoglobin, can you see hem? So it's iron, that iron metal that is there. So hematite. So bauxite is aluminium. Duralumine is not an ore. It's not. It's an alloy. All right, an alloy that contains aluminium, copper, magnesium, and manganese. All right, aluminium, copper, magnesium, and manganese. So it's usually metal that is very light. Okay, so that is an alloy. What's an alloy? An alloy is just when you have a parent metal, just like aluminum, you now want to improve its properties. All right, you now add another metal. You melt this metal, you melt all the other stuff, you mix them together. So all alloys are a mixture. They are not chemical reaction. They just reinforce the property of one another. All right. So let's see this. Which of the following is the mixture? As simple as it is, it's important for you to know that it comes out. This is the exact question from JAMB too. So a mixture does not have a formula. All right, but it's not that easy, but you have to look at it. Which of the following is a mixture? Soap. Soap is the compound. Most of you don't know. You think like, man, soap has this a mixture. Of course, the soap you are using, but what we call soap in chemistry is that primary soap without adding aroma or anything with it. So that soap is usually the sodium salt. Let's say this or potassium salt. If it is sodium soap or potassium soap, look at that. This is usually softer than that sodium. All right. So this R is now long alkyl chain from fatty acids. Okay, it's very long. So it can be palmitic acid from palm oil, right? So all those long fatty acids, when you boil it with an alkali, like sodium hydroxide, that the saponification will take place and the soap will form. That will be the formula. And this something like C17H, let it be a simple alkane and COH. Can you see how C17, how long it is? So soap is a compound. It has a chemical formula. Sand is also a compound. What's the formula? SiO2. Bronze is an alloy. Like I just said, any alloy uh, is a mixture. All right. Bronze is copper and tin. Brass is copper and zinc. Soda ash, because it's looking ash, is sodium carbonate actually. And hydrous sodium carbonate called soda ash. Just know that when we say caustic soda is NaOH. Caustic potash is KOH. Quick lime, CO. Lime water, COH2, aqueous. Slake lime, COH2, S, just little amount of water. All right, we have a lot of compounds like this that you have to know. Soda ash is Na2CO3. Sodium bicarbonate or baking soda is NaHCO3. Okay. Washing soda is Na2CO3.NH2O. We have the more you surpass such, the more you begin to know some of these their trivia names. Like I have told you, JAM can use trivia names for you, not necessarily all the time atomic part name. All right, question 7. The number of replaceable hydrogen ion in a molecule of an acid is termed basicity. All right, basicity. That is it. Atomicity is the number of atoms present in an. For example, ozone, the number of atoms is 3. So atomicity is 3. All right, oxygen, the number of atoms is 2. Atomicity is 3. Phosphorus, the number of atoms is 4. Atomicity is 4. All right, so atomicity is 2 here for oxygen, 3 for ozone. So that's what we call. But number of replaceable hydrogen ion, HCl, when you dissociate it, so only one hydrogen ion is there. So that is basicity. It's 1. All right. If you have H2SO4, for that formula to form, you have SO4 2 minus, then H plus or 2 of it, so can let you go of that. All right. So that is it. That's basicity. Like I always remind you about that basicity. If you see H3PO4, H3PO4 is phosphoric acid. Basicity is 3. But H3PO3, that is phosphorus acid, that is triisophosphate 3 acid, tetraisophosphate 5 acid. Basicity is 2. Can you see H3H3? So it doesn't mean that every time you see the number of hydrogen, that is basicity. No, it just looks like that for this guy, and this guy. For example, you may need to know the structure. If I want to draw the structure of H3PO4 now, P is, okay, look at that, double bond O, then OH, OH, and OH. This O, let me put H here. That's how they look. H here. OH. All this H can easily leave. The oxygen is withdrawing electrons, making this bond weak, and then hydrogen can easily leave. So these 3 hydrogen, they are acidic protons, they can easily leave. All right, this bond can easily break, and then that's why they have 3 there. If it is H3PO3, look at that. Only has OH2. Okay. So this is the H. Can you see? This H3PO what? PO3. Can you see that? H3PO3. So this is the 1H, 2H. So this one is not ionizable. All right. So just take note, it's not ionizable. So because of the fact that it's not that polar, P and H. So only these two can easily leave and get ionized. So that's why the basicity of H3PO3 is 2, not 3. But you are saying 3 there. You've known this for a long time, but you don't just take notes. Look at the CH3COH. That is ethanoic acid. It has 4 hydrogen, but only this OH is ionizable. Because for it to form salt, it must be CH3COH. So only 1H plus is ionizable. So CH3COO minus. So that's why the fact that it has this 3. For you to remove this one of these hydrogen, you have to do a lot of work. Okay, laboratory work. All right, question 8. What is the name given to an oxide which exhibits acidic and basic properties? That is amphoteric oxide. All right, something like zinc oxide and aluminum oxide. Okay, so they can react with acid to form salt and water. They can react with base also to form complex salt. All right. Just like this guy can react with, if I react with the HCl, you can see that I can easily form zinc Cl and H2O. So it can also form this. Okay. So this is the third complex salt. All right. When react with a base. So they can both behave like an acid and a base. They behave like an acid when they react with a base. They behave like a base when they react to an acid. So they have both basic and metallic properties, and that is amphoteric oxide, zinc oxide, and aluminum oxide. All right, question 9. Which of the following gases will diffuse fastest? Will diffuse fastest. So we have related by Graham's law of diffusion that the rate of diffusion of a gas is inverse proportional to the molecular mass. That means how heavy the compound is will make the rate. If it's so heavy, the rate at which you diffuse move from one point to the other. When you spray your perfume, all right, from one end, because it's light, the molecule can easily travel to the other side, all right? So the lighter, the higher the rate. So let's see the lightest substance here. Propane is C3H 2 times 3, that is 6 plus 2. C3H8. I hope you have seen that. So if you calculate the molecular mass, that is 3 times 12. Okay, 3 times what? 3 times 12 plus 8. That is 36 plus 8. And that is what? 44. Isn't it? Is it not 44? All right. So oxygen is just O2, 2 times 16. That is 32. The ammonia is NH3. That is 14 plus 3. That is 17. All right. When methane is CH4. That is 12 plus 4, which is 16. So methane is the lightest. So it's going to diffuse fastest. All right. So the answer is methane. All right. We're getting closer to the end of the show. So question 10, give the IUPAC name for the compound below. All right. Because of this guy that you see COH, that makes it a carboxylic acid. Let's see how many carbon. This is the functional group carbon is the first carbon. 1, 2, 3, 4, 5. That is from there. I can also go 1, 2. Let me pick another color of pen and say 1, 1, 2, 3, 4, 5, 6. Okay, so this is the way to go. Keep moving, riding on carbon chain. So that is 6. So that shows that it's hexanoic acid. Hexanoic acid. All right, I hope you have seen that. Now, this is now a substituent, and this one, since we have taken that route, okay. This is bromo. We'll name it first. 1, 2, 3, 4. So it's going to be 4 bromo. Okay. Then methyl is this one that I named 5 here because I've moved along that route. So this is 5, 5. This is still on 4 carbon, the fourth carbon. Okay, this is the fourth carbon. Can you see this methyl group is attached to the carbon number 4? Both Br and CH3 are on carbon number 4. So 4 methyl, 4 bromo, 4 methyl. All right. Why did I name bromo first? Because B comes before M. Whenever we have substituents of different kinds, we name them in alphabetical order. So that is in alphabetical order. So 4 bromo, 4 methyl hexanoic acid. Okay, so that is the answer there. Okay, so let's move. The 5. So we still have lots of questions. Okay, the number of atoms in one molecule of an element is atomicity. We just talked about it. Ozone, oxygen, only oxygen is there, so we have 3. So oxygen, that is 2. Phosphorus, that is 4. Atomicity is 4, like that. Neon, that is 1. So that is that. Okay, I hope that is clear. So which of the following reduces the energy barrier of a reversible reaction equilibrium by providing an alternative route? Okay, that defines catalyst. All right, let me give you an example. If you have this, all right, okay, this is an endothermic reaction. The reactant wants to form products, so you have to jump over this. So from this apex to this reactant level, that is what we call activation energy. Okay, and sometimes we call it energy barrier because that is the energy you must overcome for you to form B. You want to move from here. Okay, see you here. You want to get to this place. This is your destiny. Okay, so you have to jump over. So the first thing just like something that will prepare you, okay, and all that. Okay, but the main thing that actually does that affect this by providing an alternative route is catalyst. Can you see this alternative route and it has lowered the activation energy? So when you see that definition of something that reduces activation energy is actually catalyst, don't joke with it. The rest we're going to talk about it possibly when we discuss chemical equilibrium and how this affects rate of chemical reaction. The degree of disorderliness or randomness in the chemical system is called entropy. All right, that means how disorder. Look at this. The orderliness in solid, they are so ordered. So that means entropy is what? It's very low there because the degree of disorderliness, how you scatter your house, that is how we rate you. So that is the whole we're talking about, this scattering of the atoms in the chemical system. Look at gases. They are so scattered. So the degree of the randomness or disorderliness is very high. So when we talk about solid, liquid, and gas. So this has the highest disordered system. So that means the entropy is the highest here, medium in liquid and lowest in solid. I hope that is clear. All right, let's quickly go on. Which of the following reagent can be used to distinguish between ethane and ethyne? Or I mention it in a way that ammonia, gas, copper 1 chloride. Silver nitrate solution also can be used. Please take note. Lime water is to test for carbon dioxide, turns milky. Bromine water can, both of them will discolorize bromine water. While acidified KMNO for both of them will change it to colorless. All right. But this is the only reagent that can be used to distinguish between alkene and alkyne, but only terminal alkynes will produce this a precipitate with this guy. And ethine is the terminal alkyne. What is the terminal alkyne? An alkyne with the triple bond at the end of the chain. Of course, this only has two carbons, so the triple bond is at the end of the chain. Well, let's see question 5. Which of the following is not among the factors that determine the spontaneity of reaction? What does it mean for reaction to be spontaneous? It means that reaction does not need your help. No external force is needed for reaction to take place. So we have three main factors: enthalpy, entropy, and free energy change. And they are related with this equation. You see that? You must have seen this before. So this is entropy, this is enthalpy, and this is free energy change. All right. So if delta G is 0, the reaction is in equilibrium, then you have delta H equals to delta T. And so change in entropy will now be enthalpy over temperature. That is the formula for calculating the entropy. I hope you have seen that. If delta G is negative, it shows that the reaction is spontaneous. So that means that delta H will have to be less than T delta S, temperature and delta S, for this delta G to be negative. All right, if delta G is positive, that shows that reaction is not spontaneous. It doesn't mean it cannot take place. It just needs external force for the reaction to take place. We have to increase the temperature and all. All right, so the answer to this is hydration energy. So enthalpy, entropy, and free energy change in units. All right. So the next one, which sulfur is extracted industrially by frac process. I've already mentioned that before. All right, that is how it works. Please pay attention very well. The catalyst used in hydrogenation of oil is nickel catalyst. In fact, I also mentioned it. That's the point of talking about stuff. All right, talking about some bigger scope, talking about all the options. So we're not just talking about just few of them. We are mentioning for example, finely divided iron catalyst used in the ABRA process. Nickel is used in addition of oil. Vanadium 5 oxide is in contact process by producing sulfuric acid. And I want to believe that you remember contact process. Sulfur is first of all burnt in oxygen from SO2. That is the first step. The second step is SO2 will burn in oxygen. This is a reversible reaction and the most important one from SO3. All right, balance that. So this is the one that requires temperature requirement, pressure requirement, and catalyst V2O5. Then the third step is supposed to be SO3 plus H2O to form H2SO4. But this route is very dangerous, very dangerous. We don't use it because it's highly exothermic, meaning that the heat produced is enough to boil water into vapor immediately, and all the acid vapor will be in the factory. So what we do is just we just add that SO3 with already prepared little SO H2SO4. So it now forms a very thick liquid H2S2O7 called oleum. All right. Then the oleum will now be the one to dissolve in water. This one is calm and H2SO4 will be formed. Okay. So this one is not a step that we explore, but it's actually possible to produce H2SO4 from there, but it's very dangerous. And we go through the other routes. All right. So that is like that. Don't forget that. Which of the following products is obtained when excess ethanol reacts with concentrated H2SO4 at all right? Let's before react H2SO4, C2H5OH plus H2SO4. You form C2H5HSO4 plus H2O. All right, this H2O, one H and one H. So you get C2H5HSO4. All right. So this is ethyl hydrogen tetraoxosulfate 6. Ethyl hydrogen tetraoxosulfate 6, C2H5HSO4. So in the second step, C2H5HSO4 we now decompose to form C2H4 plus H2SO4. All right, look at the C2H4 plus H2SO4. So that is when the acid is in excess, when this acid is in excess. But now it's excess ethanol. So the first step will still take place. All right, but instead of this second step to produce ethane, ethane will not form because this product will now react with excess ethanol, C2H5HSO4 plus C2H5OH. We now form C2H5O. Can you see C2H5O? Another C2H5 plus H2SO4. So this is what we call ethoxyethane. It is ether. That's another class of organic compound. ROR, alkyl group, O and alkyl group. So the first step is still the same, this first step for both. But if you are producing ethane, that shows that your acid must be in excess, 1:2. Can you see that? So ethoxyethane is formed when the temperature is not 170 degrees, lower than that. Okay, this first condition is for 170 degrees. One temperature is lower than that, and ethanol is in excess. You form ethoxyethane. Let me say that again. Ethanol reacts with H2SO4. We call it a dehydration reaction. It removes water from it to form ethane. Just remove H2O from C2H5OH. You feel that ethane is what happens. So, but the reaction occurs in two steps. But the condition is temperature at 170 degrees C, and the H2SO4 is in excess. If H2SO is not in excess and it's ethanol that is in excess and the temperature is lower, all right, less than this 170, then another compound belonging to the homologous series ether will be formed. And this is ethoxyethane. All right, so that is the compound that will be formed. All right, let's move again. Question 9. Which of the following is not correct about ethane dioic acid? It's better to write ethane dioic acid first. Right, that is what I've told you. Whenever they say which of the following is not correct, don't go into the option. They will get you confused. Write the compound out and look at it, and that's where they ask the question from. It ionizes partially in solution because it's an alkalic acid. That shows that it's correct. It's a weak acid. It reacts with carbonates to give off CO2. All acids, whether organic or inorganic, they react with carbonate to give off CO2. It has 4 hydrogen atoms. Can you see? This is 2 hydrogen atoms. For some of you that may want to see the structure, the real structure is double bond O OH. All the carbon is still. I can put O here. It's still You see that? Okay. Can you see that bond around carbon is 4? Fine. And it only has 2 hydrogen. So that is not correct. Let's see whether it turns blue, not super red. Of course, all acids they do that. So that's the answer for that. It has 2, not 4 hydrogen per molecule. All right. The product of electrolysis of dilute sodium chloride solution using inert electrodes. What is the purpose of using inert electrodes, just like platinum and carbon, so that it will not react with your product? Okay, so sodium chloride is dilute. So let's say NaCl, we split it into Na plus and Cl minus. Then H2O is present, we go into H plus and OH minus. All right. So when these two are competing at the cathode is a negative electrode, so they move there. Why this is the negative electrode, they move to the anode, which is a positive electrode. Okay. So when these two are competing, you'll find out that hydrogen will be preferentially discharged. Okay. So hydrogen will come out of solution because it's lower in the electrochemical, it's less reactive. So like sodium pushing it out. So this reaction takes place twice. So let's add it together. 2H2 plus 2H plus 2 electron will give you hydrogen gas. So hydrogen will be at the cathode. They didn't mention it there, but what are the products? Hydrogen is there. Hydrogen and what? When these two are competing, OH will be potentially discharged. When OH is discharged, that is OH minus. That means oxygen is discharged. Oxygen is given off when OH is discharged. So we have hydrogen and oxygen. All right. So that is it. Some of you may want to ask, sir, so show us how will you get oxygen from this? Just write OH minus, okay, to OH. Okay, that is the neutral OH. So where the electron will be is there. All right. So if you have another OH, so many of OH minus are there, so plus electron. So you have another OH, okay. So many of OH minus. I'm just telling you that. Can you see that? So look at this. How many of OH I have there? I have 4 OH minus. Very simple. Now look at what I have done here. OH and H, that is H2. OH and H, that is another H2. So that is 2H2O, all right? So then O2 plus 4 electrons. So we can see that OH gas is giving up, all right? So this is the equation for the anodic half equation, why this is cathodic half equation. So hydrogen and oxygen are given up, all right? That's electrolysis. All right, the last part, which is day 6, we have 10 questions down. The relatively high boiling point of alkanols are due to hydrogen bonding actually affect 2 things, the structure and also the boiling point. Please take note. All right, so the boiling point is stated here. All right, it's the boiling point of water that makes the ice to be able to flow. The ice to be able to flow on water. So that is, let me show you why the boiling point actually corresponds to why the hydrogen bonding corresponds to high boiling point. For example, this is a canal, ROH. I want to represent it like this. So we have already seen that our hydrogen bonding is intermolecular bonding, like one molecule of ethanol to another molecule, not in between. Covalent molecules are inherently covalent within the molecule. That means the bond inside the molecule. Like this bond now, ROH, this one, they are covalent bond. But between one, let's say ethanol and another ethanol, that is intermolecular. You see that oxygen is electronegative, so it's going to pull electrons around this guy. So that dotted line is hydrogen bonding. If I have another ROH, let me put it like this now. This one will also join to this. All right, let's assume I put this in a container and I decide to put heat here. All right. So what will happen is that I'm supposed to just boil off each of these to convert them to vapor, but I will add extra energy in breaking this hydrogen bond. First of all, I have to break them. They want some set of energy will go into breaking, all right, first, before you now start from the scratch to start evaporating them, all right? So that extra energy is what corresponds to higher boiling point. So you break the hydrogen bond first, and you continue heating before the substance will now start boiling. So that's the reason why hydrogen bonding corresponds to high boiling point. I hope you got that. All right, so question two. In electroplating of steel using chromium, steel is the all right. So what we're just saying is this. Let's say this is your cup. All right, you can see some nice cup that you want to electroplate. You want to plate gold on it or place silver on it. All right, place silver on it. So what you would do is you would first of all you will take this, you connect it. All right. So you will take this, and you will hello this. So please, you will take this and let's just look at this. Look at this. In the electroplating of steel using chromium, the steel is the look at that. We want to electroplate this cup. That means a metal will have to be coated on it. So the metal must come to the cathode because that's where they go. Cathode is a negative electrode. So what you want to plate must be the cathode because the metal will come and stay there. That is where metal go. All right. So that is the first thing you need to know. So the substance to be coated will be used as the cathode. The metal I want to use to coat it will be the anode. Please take note. And the electrolyte will be the soluble salt of the metal anode. For example, let's say I want to do- coat this with silver to make it slippery. I use silver as my anode and cathode as my container that I want to electroplate. So the silver, the salt, the electrolyte I'm going to use must be soluble salt of silver. So AgNO3. So if you say AgCl, no, because it's not soluble. So that's what we're saying. So you use the soluble salt of the anode. Then what you want to coat, you will use as cathode. So we are here in the replacing of steel. We are coating steel with chromium. Chromium will be used as the anode. Then the chromium salt that is soluble will be used as electrolyte, while the steel will be used as cathode. I hope you get that. All right, if you want to coat your teeth with color too, like that, that's how to do it. All right, so let's see this. The manufacture of ammonia by the reaction, this reaction is TN2 plus 3H2 will give you 2NH3. All right, so and delta H is negative. That is minus 92. That's all I need. So they say the amount of ammonia from hydrogen will increase. So what will make this amount to increase? That's what we want to talk about. What will make it to increase? This what will make it to increase? Because delta H is negative, the heat is already being given out. So there will be a decrease in temperature, all right, for an exothermic reaction. That is number one. That ammonia will form normally. All right. Before, in terms of pressure, this is one, this is three, and this is two. You can see 4 moles are in the reactant side. Why two? Okay, so this is like 4 volume and 2 volume. So in the reactant is 4. So the high pressure will match lower volume because the relationship between volume and pressure is this. So wherever you have lower volume, high pressure will favor that side. So in the ammonia side, we have lower volume. So we have high pressure. All right. So in terms of what's next, the concentration, you continue to increase concentration of this reactant so that more products will be formed, or you continually remove ammonia so it won't split back into the reactant. So let's see which one is right here. The pressure is decreased. The answer is no. The temperature increased. No. The temperature decreases. Yes. Okay, a catalyst is used. A catalyst only, let me show you something. Some of you think that more ammonia will form when the catalyst. No, catalyst uh gives you shorter time to reach the equilibrium. It affects the both reaction in the same way, both backward and forward reaction. All right, it will just let you form ammonia quickly and let ammonia split back as quickly as possible. So it just to reduce the time. All right, so that is it at which you get to that. All right, so number of atoms in 1 mole of a substance. Number of atoms in 1 mole of a substance is Avogadro's number. All right, 1 mole of every substance has 6.0 times 10 to the power 23 atoms or molecules or particles. We can say that. So that is Avogadro's number. All right. So 60 cm cube of hydrogen is packed with 20 cm cube of oxygen. The total volume of residual gases. We've seen questions like this, but it's not exactly like that. All right. I've told you that balance it first and get the volume ratio. All right. So that shows that if you have 2 cm cube of hydrogen, to only pick 1 volume of oxygen and then 2 volume of this will be formed. Now they give us 60 and 20. All right. 60 and 20. So and then what do we do with 60 and 20? Remember, it must be 2:1. 40 of this will be used and 20 of this will be used. All right, and 40 of this will be formed. So for us to have 2:1:2. I hope you got that. All right, but you know that one gas is in excess, and that is hydrogen. Hydrogen 40 is used, 20 will be in excess. So when you mix these two together, so you're going to get 40 of the H2O plus 20 of the unreacted hydrogen, which is in excess. So 40 plus 20 is 60. That is the volume of the total volume of the residual gases that will be in this container. Because 40 of hydrogen will combine with 20 of oxygen and they'll be destroyed completely. And they form 40 of water, 2:1:2. 20 of hydrogen is now in excess. All right, I hope you can see that. So we have 60. And that is the total volume. That is why it is A. You can start marking yourself and see what you have got. So 5 cm cube of saturated solution of sodium chloride at that. So what do we do? That is solubility. Solubility, I can give you this formula so easily because this is not the main class for teaching. Mass of solute over molecular mass times 1,000 over volume of solvent. It's just like mole per dm cube. Mass over molecular mass will give you mole, then divide the volume. You know, that will be volume over 1,000. By the time you raise it, it forms it. So the same thing, mole per dm cube. So what's the molar mass of the salt given? 1.95 grams over molar mass of salt is just NaCl. What is NaCl? That is 23 plus 35.5. 35.5, that is 58.5. 58.5 times 1,000 over what is V? 5. So what is that? Quickly point your calculator. All right, we're going to get what? That is 6.67 mole per dm cube. All right, so this is it. Then number 7, we're gradually getting to the. So calculate the half-life of a first order reaction given a rate constant of that. All right, so the half-life is usually in 2 over the rate constant. All right, for that first order reaction. So in 2 is 0.693. All right, over that is 4.5 times 10 to the power minus 3. So it's like 0.693 over 0.0045. It's still the same thing, 4 times 5. So just press this. You're going to get 154 seconds. All right. So that's the answer. All right. Most of the time in radioactivity, they don't give you any equation more than this. The highest thing they can even talk about is the radioactive material at the beginning. If the half-life is this, so what will be the fraction remaining after? So there are simple calculations. I will soon put up some videos with the activity. All right, which of the following is an example of a chemical change? A chemical change is not easily reversible. All right, if you dissolve salt in water, it's reversible. All right, because you can evaporate the dryness. Rusting of iron, something else has formed. Iron usually reacts with oxygen and then some presence of moisture. They will form another brown substance that we don't even know the number of water molecule there. Okay, so this is a permanent change. If your gate to your house is rusted already. What you're doing when you clean it up, it's not like you have transformed it. You have actually destroyed you scrape off the iron 3 oxide that is rusted so you can see the new one. So it has eaten up the substance from iron to iron 3. So this is another compound form entirely. So melting of ice, you can freeze it back. Separation of mixture by distillation. Of course, all these separation techniques are physical processes. All right, B, I hope you're noting all this. Ammonia gas is normally dried with quicklime. All right. So it reacts with others, like usually this form ammonium sulfate and others. So quicklime, that is CaO, is the best drying agent for ammonia. All right. The alkanol that will not readily undergo oxidation is all right. Primary alkanol, they are oxidized to alkana, that is aldehyde, then to alkanoic acid, that is carboxylic acid. All right. Then secondary alkanol. I say primary alkanol, they oxidize to this. Secondary alkanol, they are oxidized to alkanone. That is what some people call ketone, all right? That's ketone actually, so alkanone. Then tertiary alkanol, they are not oxidizable, all right? So which one is tertiary alkanol here? Which one is tertiary alkanol? I've told you that a primary alkanol only has one carbon attached to the carbon that is carrying hydrogen. If you look at this one very well, you have CH2 here, you have CH3, only one carbon for the A option. This one carbon is attached to the carbon that carries hydrogen. In this one, we have CH, OH, then we have CH32. That is it. So two carbon atoms are attached to this. So that is secondary alkanol. Secondary alkanol, this one will oxidize to ethanol to ethanol to ethanoic acid. This is secondary alkanol. So to alkanone, all right? That is like propan-2. This is a primary alkanol as well, although it's a diol. All right, it's like CH2OH, CH2OH. That is it. So it's still like primary alkanol. If you look at the carbon carrying the hydroxyl group, only one carbon is attached to it. But of course, it's going to be this one that is not oxidizing. It's going to be tertiary alkanol. Let's look at the COH. Then we have CH3 in three places. Can you see that? So we have three carbon atoms attached to these carbons. Tertiary alkanols are not easily oxidized. Right. So that is the end of week 1. And congratulations once again, Marianne, for being the winner for this challenge. All right, week 2 is already started today. So what will happen is not only one person will be rewarded this week. We have 2 people that will be rewarded. Remember, we have conditions for you to win the reward. Number 1, you must submit your question, must be consistent. I'm not just answering for a day. We have 6 days, Monday to Friday. All right, Wednesday to Saturday, that is 6 days. On Sunday, we'll pick the winner, and then that is the cycle. And we're going to continue to the end of WAEC. All right. So remember that 2 people will be selected at the end of the week, and it's going to be sponsored by a former student of mine who was the head girl that finished around maybe 2014 or 2013. She was the head girl and a very good chemistry student. So she's saying that she's going to sponsor 2 students. All right, by Saturday, each of you will win 5,000, just like Marianne just won for this week. All right, so that is beautiful. We're not going to stop at the end of your work. So you better get to work and start dropping your answers. Like I've said, the most rewarding part is not that money. It's the fact that you're interacting with the questions and you're learning the concepts embedded in each question. Okay, that is just it. The incentive is just to reward your hard work. All right. Sometimes you can even use it to buy the pen, the calculator, like the one that you see on your screen, to practice with. A lot of things you can do with it. So it's very important for you to know that. So don't waste this opportunity. Let's keep copying our answers and sharing it. Like I've said, the conditions: number 1, make sure you answer all the questions, 10 questions, daily in a single comment. The second one, follow the account, and the third one, share to your friends. All right. So let's call it a wrap here. It's been a long day solving 60 questions. All right. I don't know how many, the length of time we have spent now. All right. So remember, another questions will be dropped on Monday, from Monday to Saturday. Thank you very much, and keep working out.